Hello, this is Mr. Kunk.
And Mr. Hine.
We're here to present the Music Science Math lesson for STEAM Day 2018.
The first thing you'll want to do is divide into groups. You should have enough materials for groups of about 4 to 6. But you don't need those materials yet. Those will be passed out later. So for now, just get into groups based on however your teacher would like you to do it. Go ahead and pause the video here while you do that, and then continue when everybody's in a group.
To start off the lesson, have the students discuss the following questions. What is sound? What is noise? And what is music? And what makes one different from the other? Have them come up with their own definitions for each 3 terms.
So here are the official definitions, but as long as you came up with something close, you're on the right track for this lesson. We'll start with sound. Sound is something that is perceived by our eardrums and brains and is the result of waves of compressed air. And so an object vibrates. Those vibrations push air in a certain pattern and it hits our ears, and then our brain turns that into a sound. If it's not moving air, then it will not move our eardrums and we will not be able to hear a sound. More on how these waves work later on.
Noise, on the other hand, is more subjective. It's simply a sound that humans find annoying. And there's lots of reasons that a sound might be annoying, but here's one. There's something called consonance and dissonance when we describe sound. Consonance is when 2 sound waves add together to make something with an even relationship, an even ratio, and it sounds pleasant to the ear. When 2 sound waves or more add together in a way that clashes, that's called dissonance. On the bottom left, you can see waves that line up nicely in consonance, and on the right hand, you see wave patterns for dissonant sounds.
One specific type of noise is referred to as white noise, and this is what happens when all frequencies are played at an equal amplitude. Go ahead and watch this video for a little bit to get an idea of what that sounds like. Some people find this relaxing. Do you agree?
Music is when you take sound and organize them together in a way that's aesthetically pleasing, sounds nice. One common technique in music is to move from an area of dissonance to consonance. So there's notes or sounds in music that clash or create tension, and then they'll move to a sound that's more consonant, that's more settled and more pleasing.
In a little bit, you'll be given materials to explore what factors affect sound in music, but first you'll need a little bit of background. And so we'll begin by talking about waves. Waves are the way that sound moves, and there are certain aspects to the wave that affect how we hear the sound, so we'll talk about that.
In physical space, a sound wave is really just areas of compressed air molecules and areas of air molecules that are spaced out. The molecules that are pressed together is called compression, they're pressed together, and the area where they spread out is called rarefaction. You can also graph this compression and rarefaction on a line graph, and then that's the wave that you see at the lower portion of your screen, and you see the crest or the top point of the wave above the medium position, the mean position. And that's where the compression happens, and then you see the trough, the lower point, and that's where the rarefaction would happen. So you see it oscillating or moving back and forth between compression and rarefaction.
You can actually visualize sound waves by using a slinky. And we're going to do this in a little bit. Your teacher will hand out some slinkies. There's not quite enough for every group, so some groups will have to take turns. But when you have one, go ahead and lay it out on the floor or on the surface of a big table Two members of your group should each take one end of the slinky and stretch it out gently. Be careful not to overstretch it, twist it, or tangle it, because that will damage your slinky. Once you have it stretched out, one person holding it should quickly push forward on the slinky without letting go. This is going to create a compression that moves down the length of the slinky. And that's what a sound wave actually looks like. Your hand is basically causing a vibration that moves through the slinky. There's going to be areas where the coils are close together, that's called a compression, and areas where they're spread apart, that's the rarefaction. And the same exact thing is happening with sound waves, it's just going through air molecules instead. Go ahead and try this out on your own. On a stringed instrument, when a string is vibrating, you can actually see the energy moving through the string as a wave, and it looks like that graph we saw earlier of the transverse wave. Here we have a violin that's being played that's been slowed down a lot. Take a look at the video and observe the waves moving through the string.
Now I'll have each group discuss the following question. The question is, can you hear sound in deep space? Make sure students think about how sound travels through space and what is necessary, and see if they can come up with the solution, which is on the next slide.
Hopefully your group arrived at the correct answer. The short answer here is nope. The reason why is that, as we said earlier, sound needs some sort of medium to travel through, which means it needs some form of matter, something with molecules in it. In space, there is no air or any other form of matter, so sound will not be able to move. This makes it different from an electromagnetic wave, which is light. These do not need matter to travel through, so they can easily travel through space, which is good because that allows light and warmth to come from the sun to Earth. Sound, however, does not have this ability.
Next, we're going to talk about the graphic form of a wave, or when you graph a wave. And there's certain terms that you need to know to explain those waveforms. The first term is wavelength, and that's the distance from one crest of the wave to the next. And wavelength describes the frequency of a vibration, or how quickly something is vibrating, how quickly the string vibrates back and forth. The other term is amplitude, and that's the height of the wave, and that tells you how much energy is in the wave. So a wave with higher amplitude would sound louder.
And so frequency, again, is related to pitch, and that is how high or low a sound is. And it's measured in this unit called hertz. 1 hertz is essentially equal to a vibration per second. We humans can hear something within the range of about 20 to 20,000 hertz. There are animals out there that can hear much higher sounds than this. For example, dogs or bats are able to hear really high-pitched sounds that we would not even be able to perceive. We're going to test this in the next slide.
All right, this is a YouTube video that plays the complete range of human hearing. So you can play the video. The speakers on your device may not be sensitive enough to play the very low or very high frequencies, so just be patient and give it some time and see when you can start to perceive the frequency. It may be later on in the series. You may not be able to hear the 20 hertz either from your ears or because the speaker isn't sensitive enough to play it, but it will continue through the whole range up to 20,000 and hear how those different sounds seem to you.
Here's another fun video, and again we can see how sound is actually traveling as a wave. This video has been taken from the inside of a guitar, and we can see the strings moving in that wave pattern that we saw earlier.
You'll also notice that the higher strings, or the thinner strings, will vibrate with a shorter wavelength and therefore a higher frequency compared to the lower, thicker strings on the left side. Now we've come to the hands-on portion of our lesson. Go ahead and hand out the popsicle sticks and rubber bands to the different groups, and hopefully your classroom also has one of the prototype guitars with a 2x4 and some strings strewn across it. Have the students manipulate that and note their observations on how the following variables affect pitch. How does the length of the string affect the pitch? Does a longer or shorter string make the note go higher or lower? The amount of tension, or how tight the string is pulled? And what about the thickness of the string? Is a thicker string, does that create a higher or lower pitch? One thing we won't be able to test today is the density of the string, but see if students can do a mind experiment and see, would a string with more matter that was denser, would that vibrate faster or slower? Would it have a higher or lower pitch?
All right, so now that you have had time to experiment, here is what you should have seen. When you change the length of the string, you should have seen that shorter strings will have a higher frequency, and that means they produce a higher pitch. And you may have seen that if you double the length of the string, you have the frequency. In musical terms, that means you would go down an octave. When you change tension, you should have seen that strings that have more tension or are pulled more tightly vibrate more quickly, and that gives them a higher frequency and a higher pitch. This is the reason why violins and guitars have tuning pegs, so that you can change the tension in order to change the pitch of that string. When looking at thickness, you should have seen that thicker strings have more mass, and if it has more mass, that means it's going to require more energy to vibrate. And that means that the thicker strings will produce a lower frequency and a lower sound. And finally, if you were thinking about density, you should have come to the conclusion that if a string is more dense, then it has more mass inside of it. And if it has more mass inside of it, it's once again going to produce a lower frequency and a lower sound. Now that you've experimented and know what factors will affect your instrument, we have a challenge for you. Your class was provided with a tuning fork, and that tuning fork will play a specific frequency. It's going to be your job to manipulate your instrument so that it is able to duplicate that pitch. Some tips on the tuning forks: they should only be struck against soft objects such as a rubber mallet if you were provided with one, or the underside of your shoe. You should not hit them against hard surfaces. That could potentially damage them. After you strike the fork, it might not be playing very loudly, but if you hold it next to your ear, you'll get a very clear idea of the sound. So try and match that pitch using the knowledge that you've gained today, and good luck. If you have more time, then here is a bonus challenge. We invite you to think about overtones. And so when we're thinking about overtones, common instruments don't really have a pure wave. It's more of a mixture of a bunch of different waves that create the one composite wave that we hear as sound.
On the charts on the bottom, you can see the very top wave would be called the fundamental, which is the note that you would perceive with your ears, and it's the lowest. And then the other smaller waves, they would represent the overtones that are inside the complete sound or complete wave, and these, you do perceive these as a change in the quality of the sound. Like a trumpet sounds different than a piano even if they play the same note, and that difference in quality or timbre is created by the different overtones that are present at different strengths. Overtones are kind of a tricky concept. There's a really good video here, so if you have time, go ahead and show the video. It's a really good explanation of what overtones are, how they work, and how they affect the sounds that we hear.
And so we leave you with this challenge. You can actually find the overtones in your own simple string instrument that you've created today. All you have to do is pluck the string of your instrument while gently placing another finger on the string to deaden that fundamental pitch. If you drag your finger along the string and try in different places, you should be able to isolate a few different harmonic tones. You can refer to the 2-minute 19-second mark in the overtone video for a demonstration of this process. So go ahead, try it out, see how many different overtones you can find. Alright, that concludes the lesson. We hope you enjoy the rest of STEAM Day, and have a great summer, guys.